Why do 99% of scientists believe in quantum physics? Let's find out. Welcome to the first episode of our journey into quantum physics. We're starting from zero and going all the way to expert level, breaking down mind-boggling concepts into simple, easy-to-understand ideas. But why do we even need quantum physics? To answer that, let's rewind the clock a bit. For centuries, classical physics, thanks to geniuses like Galileo and Newton, was our go-to explanation for how the universe works. It nailed everything from the motion of planets to why your ice cream falls if you drop it. But as our scientific gadgets got better and we peeked into the microscopic world, classical physics started to, well, glitch out. Experiments with light and matter revealed behaviors that classical theories just couldn't explain. Enter quantum mechanics, a whole new way to understand the universe at its most fundamental level. Quantum physics isn't just pie-in-the-sky theory. It's revolutionized technology, giving us semiconductors, lasers, and even the backbone of modern computing. Today, quantum mechanics is driving brand new breakthroughs in quantum computing, cryptography, and our understanding of the cosmos itself. In this series, we'll take you on an epic journey through these groundbreaking discoveries. We'll start with the early experiments that shattered classical physics, dive into mind-bending ideas like superposition and entanglement, and explore how modern scientists are using quantum principles to push technology beyond its limits. So, fasten your seatbelt, because we're about to take a quantum leap into the unknown.
The late 19th century marked a pivotal moment in the history of physics. Classical physics, with its elegant laws from Newton and Maxwell, seemed to explain the universe. However, cracks were appearing. Scientists were grappling with phenomena that defied classical explanations. These anomalies, like the black-body radiation problem, hinted at a deeper, stranger reality. This marked the birth of quantum physics, a radical departure from classical ideas. The quantum revolution was about to unfold, forever changing our understanding of the universe. Imagine a world where energy doesn't flow like a smooth, continuous stream. Instead, picture it coming in tiny, discrete packets like grains of sand. This is the revolutionary idea of energy quantization, the foundation of quantum physics. This new picture of the universe, though baffling at first, held the key to unlocking the secrets of the subatomic world. The quantum revolution was not merely an extension of classical physics, it was a paradigm shift, a profound change in our understanding of nature's fundamental workings. In 1900, Max Planck, a German physicist, proposed a revolutionary solution to the black-body radiation problem. Classical physics failed to explain the observed spectrum of light emitted by hot objects. Planck's solution was radical. Energy was not continuous, but came in discrete packets, or quanta. This was a seismic shift in scientific thought. The energy of these quanta was directly proportional to the frequency of the radiation, a relationship captured in his famous equation E equals hf, where h is Planck's constant. This simple equation, however, had profound implications. Planck's discovery, though initially met with skepticism, was the seed from which quantum physics grew. It was like discovering that water doesn't flow in a continuous stream, but rather as a series of individual droplets. This fundamentally changed our understanding of how energy behaves at the atomic and subatomic levels. Planck himself struggled to reconcile his theory with classical physics, but it was a pivotal step, opening the door to a new era of physics. Albert Einstein in 1905 took Planck's quantum hypothesis a step further. He used it to explain the photoelectric effect, a phenomenon where light shining on certain metals causes them to emit electrons. Classical physics couldn't explain why this effect depended on the frequency, not the intensity, of the light. Einstein proposed that light itself is quantized, existing as discrete packets of energy called photons. This explained the photoelectric effect. Only photons with enough energy, that is, high enough frequency, could knock electrons loose. Einstein's work wasn't just about light. It had profound implications for our understanding of the nature of light itself. Light, once thought of purely as a wave, now exhibited particle-like behavior. This wave-particle duality became a cornerstone of quantum physics. The idea that something could be both a wave and a particle was counterintuitive, but essential to explaining the quantum world. Section 4. The enigma of wave-particle duality. The concept of wave-particle duality is one of the most intriguing and perplexing aspects of quantum physics. It states that particles like electrons and photons can exhibit both wave-like and particle-like behavior. This duality challenges our classical intuition where things are either waves or particles. The famous double-slit experiment beautifully illustrates this duality. When electrons are fired at a barrier with two slits, they create an interference pattern on a screen behind it, a hallmark of wave behavior. However, each electron also hits the screen at a specific point, like a particle. This duality isn't limited to electrons or photons. It extends to all particles, blurring the line between waves and particles. This inherent uncertainty in knowing whether a quantum entity will behave as a wave or a particle is a fundamental aspect of the quantum world. It's not that we lack the tools to determine their nature. Rather, this wave-particle duality is an intrinsic property of quantum systems. Section 5. The Quantum Titans and Their Theories. The 1920s saw an explosion of groundbreaking work in quantum physics. Niels Bohr proposed his model of the atom where electrons orbit the nucleus in specific energy levels, explaining the discrete spectral lines of atoms. However, Bohr's model had limitations. Werner Heisenberg, with his uncertainty principle, stated that we cannot simultaneously know both the position and momentum of a particle with perfect accuracy. Erwin Schrödinger developed wave mechanics, describing the behavior of quantum particles using wave functions. Paul Dirac's equation reconciled quantum mechanics with special relativity, predicting the existence of antimatter. These pioneers of quantum mechanics, each with their unique contributions, painted a picture of a universe far stranger than anything imagined before. The deterministic, clockwork universe of classical physics gave way to a probabilistic one governed by wave functions and uncertainty. The quantum world, it seemed, was inherently uncertain, a concept that continues to challenge our intuitive understanding of reality.